So as I began to say, and probably not in an audible voice, I'm really honored to be here today, and I'm grateful to Peter for inviting me to give this opening and introductory lecture. In this 45 minutes, would like to live up to how he and the organization team have put together the Faraday discussions meeting, and that he already introduced us earlier to the wide range of topics that are covered over the next 3 exciting days. And I would like to put this in context, framed under the title CO2 utilization, why now, and how. Of course, most of the how will come through the many other presentations and in particular the discussion. But as I said, I would like to provide the framework and a broader context, if that would be useful. So let me start with defining actually what we mean with CO2 utilization, or CDU in short, for the remainder of this presentation. And I'm quoting here a new definition that is provided by the International CCU Carbon Capture Utilization Assessment Harmonization Group. Long title for a group, but I will tell you more about this a bit later in this presentation. So based on that, we understand CDU as a process including separation and removal of CO2 from the atmosphere, fuel combustion, industrial processes, or similar. Its transport via ship, train, truck, or pipeline, and its use as a resource to create valuable products. Examples could be plastics, concrete, and beverages. But what's really implied in this definition is that the utilization includes some form of chemical reaction. So by that definition, then we would exclude enhanced oil recovery or CO2 as a processing fluid, let's say for cutting or cooling. So with that, we embark into this conversation. And of course, I don't think I'm telling anyone on this call anything new about why we need carbon capture and storage and carbon dioxide utilization. In the natural balance of CO2 fluxes into and out of the atmosphere, humanity has really created an imbalance over the last, in particular, 200 years, adding billions and billions of tons of CO2 that, of course, as we all know, have a profound impact on our climate. So whether we want it or not, we have to look at the help of technology to remove some of that CO2 and deal with it. 2 major pathways, including utilization and storage. Here we are only looking at carbon utilization. And key reasons for those, of course, have been amply given and discussed in the literature, namely collated and discussed in various IPCC reports. And it's very clear that CO2 needs to be moved at very large scales now. It's really an urgent problem. It's not one of these, well, we get to it when we're ready. And the other thing that we have to keep in mind, this problem doesn't go away, because in perpetuity, we will have CO2 emissions that would pile up in the atmosphere unless we have means to somehow take care of the surplus CO2. So we keep that in mind, that we have a perpetual stream of CO2 that we need to or can actually take advantage of. And how do we do this? What are the key reasons for looking at utilization? Well, first of all, we have to realize that many of the essential products that we are using and continue to use and continue having to use are containing carbon. So that carbon in the future can come from CO2 rather than fossil carbon sources. And if we're smart about it, we can take the opportunity and develop better products so that there is actually an incentive to switch. And again, that's topic of some of the later slides. And then if we compare these utilization avenues to a storage project, we have a much better chance of financial sustainability because we're making products that actually can be sold for a profit. And the big question now is, I said already, the problem is urgent. We need to take care of it now. Is this ready for prime time? Well, if we look at scientific publication numbers as a readiness to market, we might find an answer. And let's take a step back and look at photovoltaics, technology that really has found its entry into the mainstream market, and look at how, based on the Web of Science, just searching for keyword photovoltaics shows an increase in the early 2000s in publications, tapering off then towards 2020. But if that is now connected with the deployment of photovoltaics installations, we see a clear connection to this. So taking that as a case study and looking at what's happening in the CDU space, well, here we are. Again, looking at the Web of Science, just looking at CO2 utilization, we see an increase in publication numbers, very similar to photovoltaics, but shifted in time a little backwards. So I posit that, yeah, I think this field is primed to be deployed. So, fine, CO2 as a raw material. But what can we actually make from it? What products can we make? And there's a whole list, categories of materials, starting with construction materials all the way to food, showing that there is a very large range of product categories that could be addressed, and there's an enormous potential for CO2 use. You see in the right-hand column billions of tons that can be used in lieu of fossil sources or in new products, as I will talk about in a few moments. And then, of course, given that we're making products that people need to buy or want to buy, there's a large market opportunity for that. So these are all interesting and good first steps towards CO2 utilization. But then, if I look at it from a marketing point of view, why should I switch to using CO2? I mean, we have solutions. So it's always hard to go away from something that works. But again, if we can make something that's a superior product, that certainly would be a driving force. If CO2-based products cost less than existing ones, then there's absolutely no reason why CO2 shouldn't be used. And if the transition to utilization of CO2 is easy, then manufacturers will more easily adapt to those new pathways. So let's keep some of those aspects in mind. Lastly, it's one thing if we can make products. It's another if we want to sell them. Because a sale also means that there has to be a customer. Do customers want to use CO2-based products? So what I'm sharing with you now is the result of a representative survey of adults in the United States. So that's probably important to keep in mind. 2,400 adults were surveyed about whether or not they would use products made with CO2. And more than 2/3 of them would say definitely yes, yes, or probably yes. So that actually is very encouraging to see that. There is somewhat of a product dependence. People have less hesitation to use CO2-based products if it becomes a question of furniture or plastic containers. It's a little less positive if we look at beverages, in particular if the source of the CO2 is a power plant or a chemical factory. But these results, first and foremost, I think are encouraging for technology development in that there is there's at least some emerging interest and willingness to actually use the CO2 products. So the question then is, how can we introduce these products? How can we enter a competitive landscape? Construction materials, for example, are very low margin materials. So could potentially be a very cost sensitive issue. So good news here is, if we look at construction materials, almost all of them are not made from CO2 or with CO2. So here we are actually introducing new materials, and we have the chance to introduce better materials than what exists, and that is a foot in the door. With all of the other categories, it's a mix. It could be drop-in replacements, could be new, and therefore it depends on a case-by-case basis on whether or not the competition is based on replacing what already works or actually introducing something that nobody has yet. I want to show just a couple of examples. Of course, by no means can this be comprehensive in the time that I have, but let's just start by looking at new versus drop-in products, just looking at examples with CO2 specific products that are not available as a conventional product. We can look at construction materials such as new kinds of concretes, and those can actually have properties that are unique, new, and not available so far. On the other hand, we can also just have drop-in replacements for existing use cases such as air traffic, where there is a strong push for decarbonizing air traffic. And therefore, if we had a CO2-based fuel that could replace petroleum-based fuels, that would be an interesting avenue to deploy CO2-based fuels. We can actually also look at making chemicals, making fuels that we all know, but make them with an intent for a new use case. And one example that finds growing interest amongst energy utilities is shown here. We all, of course, want renewable energy deployments to increase as rapidly as possible. But you also realize that the more our overall energy supply depends on wind and solar energy, the more we become vulnerable to intermittency. How do we buffer that? It will not work to buffer intermittency with batteries over periods that exceed hours. So we need some form of higher density energy storage, and that is a different form of chemical storage. In other words, fuels such as synthetic natural gas, ethanol, or hydrogen, amongst viable choices. So in cases of surplus renewable energy, we could switch to producing such fuels instead of selling the electricity for a negative price. So it could be put to better use. And at some point, we have to do something like that to provide continuity in energy supply. So these were sort of three cases where the introduction of CO2-based products really seems to be almost straightforward. Of course, nothing is ever straightforward, as we all know. But let me further dive into examples of such technologies, and just give you two examples out of our own university here in Michigan. First, starting with a startup company launched by Professor Setyan Mi, where they combine two technologies: the silicon wafer technology that is used to make computer chips, and on these silicon wafers, they grow nanowires made from gallium nitride, the materials that are used to produce light-emitting diodes. And in these nanowires, they can embed catalytically active materials so that in one device, in an artificial photosynthesis process, they can convert CO2 and water into methane or methanol, or can also make hydrogen just out of water. So this sort of integration of multiple steps into one can become a very efficient and robust technology that is shown here in a prototype, sort of a collection lens that focuses sunlight onto this device. Now, looking at sort of large-scale opportunities to harvest CO2 and ideally not just using it in a circular fashion, but in a permanent removal process, we need to look at building materials. We need to look at making concrete through curing concrete with CO2. We can react waste materials with CO2 and then stick those into concrete. And we can actually combine these processes with what's called bendable concrete. It's an engineered cementitious composite, which has an enhanced lifetime over regular concretes. And this is where we come back to, do we have a CO2-based product that is better than what's regular? And here is one opportunity. Because I mean, we all have seen crumbling concrete. This is a path in a city park here in Ann Arbor. Many roads look like that. We don't want this, and therefore, looking at bendable concrete like you see here in this 4-point bending test, this beam here is started out as a straight piece of concrete, and it can be bent as shown here without breaking. That's a technology that is, of course, huge interest, for example, in earthquake-prone regions. The photo here on the right shows you Japan's tallest residential tower building near Osaka, which was made with such bendable concrete. And it has survived quite a number of earthquakes without any trouble. So how does this work? Why is that bendable concrete better? It is better because even though it does develop cracks, these cracks are really, really tiny, only as wide as less than 100 micrometers. And the brittleness is typically what literally kills concrete in real applications. So if we can suppress that fracture, then lifetime is enhanced. And given that half of the concrete production goes into repair, that would be a big win from an environmental and, of course, also cost point of view. And now that the concrete doesn't break apart into small pieces but stays intact, there's actually a very interesting additional benefit from this small crack width, in that it exposes residual unreacted cement or supplementary cementitious materials, and therefore these cracks fill automatically when exposed to the environment, as you see here in this video. That sort of is an accelerated video of a 48-hour time period showing how the cracks in the concrete heal themselves, self-repair. That's an exciting opportunity, how CO2 can be utilized to address climate-related issues. We can help fix infrastructure problem with improved CO2-based materials. And of course, new technologies will require additional jobs. And if we look a little further outside of the topic of this conversation today, automation certainly will help revolutionize the whole construction industry and add jobs. So a wonderful synergy of opportunities. But CO2 is not available at the cost we needed. It's really, really hard to capture the CO2 and provide it for use. Showing here examples of existing or planned deployments, just to illustrate how large these installations have to be. And if we look at billions of tons of CO2 to be captured, we can all imagine what this means in terms of facilities to be built. And it is very clear then also, if we look at where the CO2 will actually be captured from, that CO2 is not equal CO2. The source really matters. If we pick it up from concentrated sources, let's say at fermentation plants, it's a very different story compared to isolating it from air. So different amounts of energies are needed associated with emissions, at least at present day. Post-capture processing, pressurizing, purification, etc., all important. Is it available where we need it? How much land do we need to use to capture the CO2? And what does it cost? Right? What does it cost is ultimately the bottom line. We can't do things that are too expensive, but we'll talk about this separately. And here's why. Looking at different product categories, producers certainly are willing to pay for CO2 at various levels, depending on what the value of the product is that they can make. And therefore, the price of CO2 likely will play a major role in the market introduction of CO2-based products. Right? In some higher value materials such as carbon fiber or some plastics and chemicals, even concrete curing, it's different from fuels or construction fields. Right? So that certainly is one reminder that one of the areas to work on is making CO2 capture more efficient, smaller, and cheaper. But we also have to do one thing else, and that is we have to rethink energy use broadly. Because let's not forget, CO2 is, amongst other reasons, a problem because it's such a low energy molecule. I mean, most of the things that we seek to make out of CO2 actually require enormous amounts of energy to be put into. I mean, as chemists, you all know that there's next to nothing that we couldn't make that contains carbon starting from CO2, given unlimited resources, and that includes energy. Of course, we can't afford that to the ultimatum, but we certainly need to realize that while CO2 can become a key source of carbon, we need a new paradigm for energy use, right? We cannot just say we have to minimize it to the absolute minimum because avoiding CO2 emissions supersedes the lowest possible energy use. That's hard to accept, right? After we've been trained for decades to look at energy efficiency as the one of the key and foremost criteria. But here, again, avoiding CO2 emissions is really important. So all of that in aggregate requires that we need guidance through policy, and we need policy to help drive this economy. Why? Think back to the images that I've shown you for the CO2 capture facilities. These are huge installations that will require lots of capital, and therefore policy needs to provide stability so that those who want to build these facilities can actually count on their usability, their viability in the long run. And that means providing incentives that, of course, in different countries are provided through different means. These could be taxes, these could be rebates, these could be procurement requirements, and so much more. But without this, we will not get started anytime soon. And again, let me remind you, we need to start yesterday, not today, not tomorrow. We really need to get going. And in that light, the role of net zero carbon commitments that are growing by the day is really important. Carbon neutrality commitments are being announced by entire nations, by companies, by organizations such as universities. And that has created enormous demand for carbon removal and offset markets. But we also have to realize at some point, the low-hanging fruit for offset markets are harvested. What then? Well, this is our chance. CDU can become an opportunity for such markets. And then we need to think about, okay, how do How do we count? Who claims the credits? Who pays taxes? Who tracks and certifies reports? Unanswered questions. And again, might depend on which country we are talking about. But it really is important. Because right now, it's very unclear how this all works. And it is already beginning to show that the level of confusion is high enough that one has to worry about credits being sold multiple times. Or if there's rebates, who actually has the right to acquire them. So in that context, in claiming credits, in buying offsets, it also is necessary to really know for how much have I done? How much do I actually claim as a tax rebate? How many millions of tons of CO2 have I handled? And it is very clear that many CO2 users can become carbon neutral at best. But this is still a huge win. Don't get me wrong. There are a few large-scale opportunities for possibly true negative operation. But it is fundamentally important to properly and accurately assess the life cycle emissions of a process or a product, so that there is no selective choice of boundaries or use phases if required to look at that is being omitted. That is especially critical here because we cannot make mistakes for the environment, right? This is not something that we can allow to happen. And as I put together this presentation, reflecting about this reminded me about what Sir Ricardo had talked about almost a century ago when he presented a review on internal combustion engines. In particular, he thought about a direct injection engine technologies that fundamentally provides better fuel economy, can lower emissions, and he concluded that working with a stratified charge is possible, and the high efficiency theoretically obtainable from it can be approached. The worst feature about it is that if not just right, it may be very wrong. Right? And I think the same can be true for CO2 utilization. We can actually make mistakes that are harmful for the environment, and we need to avoid this. I mean, this study that was published some years ago very nicely lines up different ways of making methanol from CO2, and it compares the global warming impact to the baseline of traditional methanol production. And it's very clear that some of the CO2-based solutions are certainly better and could be pursued. But it also is very clear that some are far, far worse. So how is that then being conveyed? How is it being put on a common platform so we can actually make these comparisons? This field has already produced thousands and thousands of studies, and comparing them is really difficult. It hasn't been a uniform process, and that can cause problems. Another example that I want to show you is seen here. If we look at the CO2 impact of CO2-sequestering concretes, if I can walk you through these diagrams, especially starting here with the left one, we're showing here a probability density function of looking at 10,000 Monte Carlo simulations of experimental data we took from the literature for 99 different concrete studies. This is an example for one of them. And we look at a variation of all the 13 guiding variables and how they will impact the total CO2 emissions for the CCU-based product in comparison to a conventional Portland cement-based concrete. This particular example shows that under all circumstances, within the uncertainty limits of the input parameters, this type of concrete is always worse than regular concrete, despite the fact that we are using CO2 to make it. Looking at details of the simulations, we can look at the sensitivity of the net CO2 benefit with respect to the 13 parameters individually and isolate which ones are the most sensitive. In this case here, these two examples, it would be CO2 injection and CO2 curing. Right? So if we do this for all 99 studies, we're getting a picture like that. That's just an eye chart. Don't look at details, but reflect on what's shown in red is worse than regular concrete. Only the green ones, less than half of all studies described in these 99 cases, actually produce a climate benefit. Right? So it's really critical that these assessments are being done, that they're being done rigorously and uniformly. And to help ensure those kind of assessments are done in that manner, we started to support a larger group of universities and institutions to collaborate on providing guidelines for techno-economic assessments and life cycle assessments for CO2 utilization, building on the ISO standards for life cycle assessments and developing similar guidelines for techno-economic assessments, but also being more specific about CO2 capture, utilization, and eventually storage, because over time, we've expanded this group, and here is this international CCU assessment harmonization group that I talked about at the beginning when I presented to you the definition of CDU. That now includes a variety of national laboratories in various countries. And this group has continued a dialogue into further harmonizing how such assessments should be done. And we invite the global community to join us in May for a series of webinars where we'd like to present what our findings and recommendations would be. But we want to have this also with an eye on hearing from the community. So how do we think about all of this now? Talked about so many different things that are connected to CO2 utilization. Ultimately, if we take a step back, we need to make sure that we get the best possible outcome for the environment. I think it's very clear that this is the ultimate motivation and driver for all of us. Clearly, to make that happen requires a lot more than just having an ideal goal. And therefore, looking at a system-wide design to assist decisions, of course, needs to start with what are viable technologies? What actually can be done? What's missing? What do we need to focus on in our research activities? I mentioned earlier that we can start looking at waste material streams as resources. And for that matter, CO2 could be understood as a waste material stream too. We don't have the supply chains, we don't have the value chains set up for that. So that all needs to be built and deployed. I have mentioned energy systems and their role in this quite a bit. And it is very clear that if we look at current energy mixes and evaluate CO2 utilization under these, many times CO2 utilization will not ever make sense in a context of environmental considerations. However, we need to look ahead. Where are we in 10, 20, 30, 40, 50 years when the energy systems have been decarbonized, defossilized, I should say. And therefore, will the technologies then do what we expect them to do? It's really critical to have that foresight and that planning ahead, and have the patience to go through the coupled deployment of CO2 utilization and supporting zero carbon energy. Nobody will build more zero carbon energy if there is no taker. So these technologies need to go hand in hand and push and pull each other until we have finally reached a fully defossilized energy system and CO2 deployment. Again, don't forget that CO2 utilization is not just a means to stabilize the climate in removing CO2 from the atmosphere. It is also a means to provide us with the essential carbon-based materials that we need to have. After all, human life is carbon-centric, right? We cannot just decide no more carbon. Let's not forget this. We of course know that transportation infrastructure is a must if we look at these enormous amounts of CO2 and the materials produced in locations that are currently not involved. And that's easier said than done, not only because it's costly, but who is in favor of building new pipelines? This is not something that the general public might actually be in tune with. Associated issues with that. How do we pay for all of that? How do we deploy a new industry that might take long times to actually generate positive revenue? This is something that really requires some deeper thought, so that the perspective is there, the stability is there, so that people engage and invest in such technologies. And therefore, policy support is really critical. And ultimately, everybody has to be on board with that. Well, everybody, at least a solid majority, because can't deploy such massive installations against the will of the people. So what I started out as a flat triangular manifold here on the right in this diagram is actually including many more dimensions. And of course, tweaking one will affect others. And therefore, the role of data science, data management, and artificial intelligence really will increase dramatically to drive CDU forward. It's really critical that we minimize global CO2 emissions. And that sometimes might mean that we do not minimize to the ultimate minimum a particular subset of the whole value chain, but we need to look at its entire value stream. At the same time, of course, we need to maximize economic value. And I want to be clear here, that economic value, that positive bottom line, nobody will be able to manufacture anything and sell it if it means a financial loss. So it could mean, at least for quite some time, public subsidies to make sure that there's overall a economic value that drives this new industry. And critically, again, reminding everyone of why we're doing this. We need to maximize social value and equity, access to the products, but also the new jobs that will be created. And that, again, requires really careful assessment of the whole system, that without these new data science tools will be really difficult to manage. And that's true also for the overall efficiency and communication in these new value chains that do not exist, value chains that built on existing installations, such as in the petrochemical industry or construction industry, but need to be adapted to new streams and new methods. Not all industries actually have adopted lean manufacturing, for example. And that will also allow us to optimize overall resources management, which is critical. We need to look at, after all, we're talking about net zero, net, globally. So we need to optimize. We need to optimize resources in a very smart manner, and that includes keeping track of who's doing what, who's claiming what, and so forth. So, given that the next 3 days will be very research focused, I still want to reflect on what an industry collaborator told me just recently, and that's this. She said, "It seems to me that there is such a canyon between what the academic world considers complete and what the industry considers emerging. It is the old valley of death," right? So the long stretch in the history of a company, early stages of company, when everything that they do comes with a financial loss. Going over that is really difficult. And it's one of the limiting steps, getting technologies out of universities into the marketplace. In parts because CDU is a hardware-based effort. To scale from a laboratory effort where we just work with a little beaker, we demonstrate that we can make things, is very different from an industrial setting where hundreds of tons or more a day of a substance have to be produced. So somewhere in between, we need facilities, entities that help bring pieces together and scale them along this entire value chain. Installations that are bigger, that allow university researchers and industry to bring things together at a scale that gives industry confidence that the technologies work and are ready for the next step. So how far have we come? From the research papers that I counted and showed you at the beginning, we see that this is a field that's not entirely new. Of course, we all know that. But how much has carbon capture and utilization and storage actually been progressing? To track that, we're introducing the carbon removal index, which is a percentage of captured CO2 in relation to a target. And if we tally up what had been captured worldwide last year, we look at a carbon removal index of just shy of 1 if we benchmark it with respect to the most recent IEA CCUS target. If we take our own global CO2 initiative goal for carbon dioxide utilization, that index would stay at just shy of 2, assuming that all of the captured CO2 was actually utilized. However, it's clear that this is not the case. Most of what has been captured last year has actually been stored, has been used in experimental facilities, or even been re-released because it was an effort to improve capture technologies. So it's very clear that this needs to be a bit more granular, but I think it's important to keep track of how much we're doing and illustrate how far we have to go. It is quite a steep curve to scale. But with that, I would like to draw this to a conclusion with some key observations in that CDU is a societal opportunity. CDU is an economic opportunity, and it is an environmental opportunity. So I'm glad to see that we're on our way, and I'm glad to see this community debate over the next 3 days to make sure we accelerate this field and bring it to full blossom. Thank you so much for joining me today, and I look forward to the discussion now and until Friday.